Hello, Link341. In this lecture, I will be talking to you from the grad student's office again, and in this lesson, we are going to learn about harmonics. Without further ado, let's start with the lecture. So, let me just set this up properly. Oops, no, I don't need that. That's good. So, every year we take a couple of drawings from our students who were drawing mid-sagittal diagrams just for fun to see how they were drawing some images of these mid-sagittal diagrams and to have some warm-up here and to relax a little bit because drawing is hard. So this one drew an interdental here, and it's a nice drawing with a little bit of protruding jaw, strong jaw, right? But these ones are, I'd say, quite exceptional. They are correct, but usually humans' head does not look like this. So take a look at those, and maybe it's not a bad idea to work on your drawing skills a little bit and to be careful with those. This one says drawing is hard. It is, but very nice retroflexivity shown, right? And this one says moral of story, tongues are effing weird. That's true, but they are very useful, and they help us speak, right? So where are we going with all of this, right? We're starting to cover acoustic phonetics. We'll start seeing what is the acoustics of the acoustic product of sounds. Since our native language influences the way we respond to other languages, it will be easier now to transcribe what you're hearing because we're going to see what's going on, right? What's happening. And finally, we've come to that part of our journey when I told you many times, well, wait, we'll see what's going on. So this is a part of acoustic phonetics in which we will observe what is going on with air pressure and with air that is being shaped by our vocal tract and that is being produced or that is being helped produced with our vocal folds. So today we will start harmonics and resonance. Next time it's not going to get any easier, but we'll make it. And note, I posted a supplementary reading on a website. It should be in handouts. Yes, additional reading, Elements of Acoustic Phonetics by Peter Ladefoged. This is for you to read as an additional reading, something that might help you understand acoustics better, right? Okay. What have we learned? So we have learned how to calculate frequency of a periodic wave. We have learned how to calculate the amplitude or RMS amplitude and intensity of a complex wave. So we've learned those things, and we'll start putting frequency and intensity together finally, right? With respect to complex waves. So yeah, that's what we're going to do today. We know that when more than one sine wave gets combined, they form a complex wave, right? We also know, and we've been doing some calculations of these, that at any given time, each wave will have some amplitude value of a sine wave 1 at time 1, amplitude value of sine wave 2 at time 1, and the amplitude value of a complex wave is the sum of these amplitude values, right? This is one complex wave example, for example, or this is one sine wave example first. So this one has high amplitude, 1, right, and low frequency because 1, 2, 3, 4 repetitions. in comparison to this one, which has high frequency but low amplitude, right? And we've talked about these. The sum is this complex waveform, right? And we'll see what it means for a waveform to be like this, right? Why is it like that? But we know, so far we know that this is the complex wave, which is the sum of these two sine waves, right? Okay, now we know that combining sine waves results in a complex periodic wave. This complex wave has a frequency which is the greatest common denominator of the frequencies of the component waves, right? Greatest common denominator is the biggest number by which you can divide both frequencies and still come up with a whole number. We know that when you have component wave 1, which is 300 Hertz, and 500 Hertz, we get a fundamental frequency, or this greatest common denominator, of 100 Hertz, because you cannot divide 300 with 200 or 500 with 200. You cannot divide them by 150. The greatest number that you can divide them, and the greatest number that has to be a whole number, it mustn't have just any decimal places, it is 100, right? And the fundamental frequency of the given wave will be 100, right? Okay, so we've shown that multiple times, but I'll show it again. So 100 Hertz wave, 1 second is good, amplitude can be the same, I don't care about it right now, but I care about this part, which is the frequency, right? Okay, so 300 and 500, and we get this guy, yeah. Oops, yeah, this is what we get. Let's start from here, for example. Okay, grab a couple of chunks. All right, so yeah, this is what you get, and the frequency or pitch, fundamental frequency here, you can see is 100 Hertz, right, all the way through. All right, great. Now that we know this, we can move on and ask the question why, right? Why is the fundamental frequency the greatest common denominator of the two? Let's flip this upside down. Think about the smallest common multiple of the periods of both of the component waves. What do I mean by this? Well, both component waves are periodic, right? They repeat themselves in time. The pattern formed by combining these component waves will only start repeating itself when both waves start repeating themselves at the same time. And this is important, right? So we want to somehow, I'll open a Word document and I'll write it down here. The pattern formed by combining these component waves will only start repeating itself when both waves start repeating themselves at the same time. Alright. The example of this are 3 Hz sine wave and 5 Hz sine wave. And I will show you this in a second, okay? What I mean by this. But it's very important to understand what I would otherwise write on a whiteboard, this little pattern here, right? Okay. We will have some more writings here. For example, starting from 0 seconds, right? A 3 Hz wave will repeat itself at 1/3 of a second. then at 1/6 of a second, and then, or sorry, with 2/3 of a second and 3/3 of a second. So it will be something like this: 1/3 of a second, then at 2/3 of a second, right, at 0.66, and finally at 1 second, right? A 5 hertz wave will repeat itself at 0.2, so 1/5 of a second, right? Then 2/5 of a second, then 3/5 of a second, then 4/5 of a second, which is 0.8, and finally at 1 second, right? Or 5/5, which is 1. To draw, maybe I'll draw, okay? So I might do something like this. So let's say the 3 hertz and 5 hertz waves. The 3 hertz waves is repeating at 0.3, right? Then it's repeating at 0.6 or 66, right? Oops. And finally at 1 second, right? So if I might create one, 1 second, frequency 3, amplitude is not important this time. Let's see what's going on here. So, right, at 0.33, right, 1 repetition. Then at 0.66, another repetition, and at 1 second, and the final repetition. 3 times. That's why the frequency is 3 cycles per second, right, or 3 hertz. All right, I'll create a 5 hertz, right, sound, pure tone. And this one repeats at 0.2, right, somewhere here, 0.2, then here, at 0.4, then here 0.6, 0.8, and finally 1 second. That's clear, right? So this one will repeat 0.2, 0.4, and a question for you would be, which one is faster, right? Not faster, or which one has higher frequency? Well, obviously, this one, the second one, because it has frequency of 5 hertz, which means it has 5 repetitions per second. And at 1 second, right, this is where they become lined up, right? And this is where they keep doing their thing, right? They keep doing their thing here. So we are pretty much they do not align at any of these middle values, right? So their periods do not align, but they align when they come to 1 second, right? So they keep doing their things, they keep repeating, right? Keep repeating themselves. And then what happens, as I said, the pattern formed by combining these component waves will only start repeating itself when they both start repeating themselves at the same time. That is at 1 second. Which means that when we combine these two, when we combine them and make a complex wave, they will only start, this pattern will only start repeating, or the complex wave will start repeating itself when they align, when they line up, right? And if we create from formula a 3 hertz and again 5 hertz, complex wave. This is what it looks like. Maybe I'll create, sorry, one with 3 seconds so that you can see clearly what's going on. So this is what it looks like. So this is one repetition, right? And it's at 1 second, right? One cycle at 1 second. Another cycle at another second, right? At second number 2. And another cycle at second number 3. So they repeat themselves. This complex wave repeats itself once in 1 second. So the frequency would therefore be, of course, 1, right? 1 hertz. And as you know, the greatest common denominator of 3 and 5 is, of course, 1, right? This is what it looks like. So you can see the 3 hertz wave. It's being repeated here at 0.33, and it does not align with this one, right? There is no alignment there at 0.66, so no alignment in time. That's what we're talking about. The time is different. They start aligning at 1 second, so they both come to 1 second, and at 1 second they start aligning. So we know what the fundamental frequency will be. And this is what it looks like. The combinations of 3 and 5 hertz waves, the period will be 1 second and the frequency will be 1 second. You now know that frequency is 1 per period and period is 1 per frequency, right? So it's it can be easily calculated, and this is what we received, right? That's it. This kind of right display. So hopefully we're clear with that, right? The importance of all of this is that each component wave will complete a whole number of periods within each period of the complex wave. And now we know the greatest common denominator. Okay, conversion. So as I said, the important part is that each component wave will complete a whole number of periods within each period of the complex wave. If we combine a 6 hertz wave with an 8 hertz wave, what should be the frequency of the resulting complex wave? And I think you know the answer to this. Now we know about the greatest common denominator, but there is another way of calculating this, and that is when we pay attention to period, right? So what would the period of the complex wave be? That's another way to think about it, and this is also important part. So each component wave will complete a whole number of periods within each period of the complex wave. So meaning that these individual waves, sine waves 3 and 5 for example, will complete a whole number of periods within each period of the complex wave. So they will do their thing until they are aligned, and they are aligning at 1 second, right? We saw that here. So they will repeat themselves, right, until we come to 1 second. And at that 1 second, we can say, okay, we have a complex wave that is being repeated now. For 6 and 8, I think you know the greatest common denominator or the period of these. So for 6, you will have 0.17 or 1/6, right? Then you might have 2/6 and so on and so forth, right? Until you get to 6/6, right? Which is 1 second, and that's somewhere, that's here, right? Okay. Here you have 1/8, 2/8, 3/8, and so on and so forth until you come to 8/8, which is 1 second, right? And there you have it here, right? So yeah, the period would be 0.5 seconds and the frequency would be 2 hertz, right? And if we try and make up a formula out of this, we will see the same thing. Okay, so let me take a look at 1 second. That's 1 second, right? So in 1 second, this one will repeat 2 times. This is 1 repetition, and this is a second repetition, right? In 3 seconds, it will repeat, I don't know, 6 times, right? So 1, 2, 3, 4, 5, 6. And that is because these are faster or have higher cycles per second, right? And they align at 1 second, or sorry, at 1 second, but they also align at 0.5 seconds. So this is where they align as well. And this is the first spot of alignment, and that's their period, 0.5, right? See here, okay? This will be their period. When you know their period, now you can easily calculate the frequency, which will be 1/2. 1 divided by period, or 0.5, sorry, but that would be 2 hertz because the calculation is different. But it's easily done. So you can also tell frequency from period and period from frequency. And that's the spot where they align for the first time. That's why we need to pay good attention to this spot, right? At 1 second, they align for the second time, so which means that their frequency will be 2 hertz. Hopefully we understand this, right? Hopefully we understand this. And again, not this one. Oops. Okay. No, sorry. Confused. And who do we owe all of this to? Well, this we owe to Joseph Fourier, who lived from 1768 to 1830. He was a French mathematician. He studied heat and periodic motion. He studied lots of other things at times when white folk were privileged, very, very privileged, and when they could study all sorts of sciences, and that was acceptable, of course. He had a weird idea by studying heat that if you leave your house wrapped up in blanket and go around places like that, you will live healthier life. One day he slipped by wearing this blanket, and we never heard of him again. But before he did that, he got an idea that any complex periodic wave can be constructed out of a combination of different sine waves, right? The sinusoidal or sine wave components of complex periodic wave are called harmonics, right? And this is a powerful idea and theorem because not only do we use it in acoustics, but it is being used to determine the chemical content and structure, consistency of stars, thousands and thousands miles away. It's used in optics, image processing, quantum mechanics, electrical engineering, and so on and so forth. In acoustic phonetics, we understand sinusoidal components of a complex periodic wave as harmonics. And you might have heard them about this in music, and that's essentially how we're going to use harmonics here as well. And I think that this is also a very nice idea that should be written down, right, on our imaginary board. So any complex periodic wave can be constructed out of a combination of different sine waves. Fourier's theorem, or you might know it as transform as well. It has different names depending on what it's used for. Mathematicians use it as transform, I think, physicists as well, and so on and so forth. So you will come across this theorem quite often, and it's a great great theorem. And if you are fans, or if you like Pink Floyd, you've probably seen these. You've probably seen this display. Pink Floyd uses it. This is a prism that breaks the light into its component photons. So the light beam comes into the prism. I think it's a glass prism, and it's broken down into as many photons as light photons as there are, or light waves, so to say. So in the same way, we are going to do the same with acoustics. We are going to do the same with a complex wave. Sound may be split up into component frequencies, just like a prism splits light up into its component frequencies. So we are going to do the same with our complex waves. And to do this, we will simplify things a bit, just like we have been doing so far. Okay, I'll go back, or I'll go to the next slide. One way to represent complex waves is with waveforms, right? So you have y-axis, which is air pressure, and x-axis, which is time, right? That's one way to represent it, and we've seen it here, right? So y-axis is the pressure or the amplitude, and this one is the time, right? 0.5 seconds. However, we have other ways of representing complex waveforms. And another way to represent a complex wave is with a power spectrum, or spectrum for short. Remember, each sine wave has two parameters, amplitude and frequency, right? And a power spectrum shows intensity, which is based on amplitude, right, on the y-axis, and frequency on the x-axis. You can easily get power spectrum so I think I have here this complex wave of I'll rename it 6 and 8, right? I think 6 and 8 hertz, right? Which would be 2 hertz frequency of the complex wave. To get a power spectrum, you will go to Analyze Spectrum, then you will go to Spectrum, and you will be shown sound to spectrum fast. You don't want to be fast, you want it to be normal. You're going to click OK, and the spectrum is here. Now you can view and edit the spectrum, right? And here you go. Yeah, let me zoom in a little bit. Okay, not cooperating with me. Let me see, maybe I went too far. Okay, yeah, no, I went too far, sorry about that. So, as you know, I created two sine waves, right? Two sine waves here. One is 6 hertz and one is 8 hertz. Both sine waves have the same amplitude. And this is the power spectrum. As you remember, the power spectrum on the y-axis, this axis, right, shows intensity, which is measured in in decibels, right? Here in decibels, right? And it's around, like, I don't know, what's this, 90 decibels. But it shows on the x-axis not the time, but it shows frequency. So you can see this frequency of this one, if I place correctly, it's 6, and this one is 8. And you remember that I created a complex wave from a sine wave of 6 and 8 hertz. So 6 and 8, and that's what the power spectrum shows. If we play it, it will play the same thing. You cannot hear it because it's very low, right? It's very low in frequency, so that's why we are unable to hear it. But we will create some new ones, okay? Okay, and for example, this is a waveform that shows amplitude or air pressure differences through time, right? For 1 second, let's say. And when you add this one and that one, you get a complex wave, right? That has this amplitude with this, within 1 second, usually. The power spectrum shows that this is an amplitude of this. I'll have to draw again. So this would be amplitude or intensity, right? It's fairly similar. Intensity. Usually in Prot you will have intensity, so you may write intensity on your assignments. Okay, intensity. And here we get frequency, right? Frequency. The frequency of this one is 1, 2, 3, 4, so it's 4, right? And the amplitude of this one is 1. Let me, oops, yeah, I'll remove it a little bit, is 1. So is this one. You can see it goes up to this point, right? 1. The amplitude of this one is much lower, like, right? It's at 0.5, or let's say 0.5, or intensity 0.5. And there is no unit here right now. We don't have unit. In Prot you will have decibels, but when you're drawing like this in two-dimensional view or display, there is no unit. 0.5, and the frequency will be, oh, sorry, no, it's 12. Yeah, 12. If you count 1, 2, 3, 4, 5, 12. 12, right? When you combine them, you get exactly these two sine waves: 4 hertz, 1 amplitude, 12 hertz, 0.5 amplitude, and that's what we call harmonics, right? Those are the harmonics of the complex wave. Component waves that make up a complex wave, right? Okay. We understood that part. I will now create a much better example for you to hear. So create from formula. I will create a complex wave of 300 hertz and 500 hertz. The amplitude will be the same. And 1 second is okay. Let's see. This is what it sounds like. It's a little bit annoying. And if we go to analyze spectrum, to spectrum, okay, view and edit, we'll see here that we have 2 of these, right? I'll try to zoom it in. We have 2 sine waves. The first sine wave is at 300 hertz, right? 300 hertz. The second sine wave is at 500 hertz, you see, on the x-axis. And the amplitude is whatever. This is 85 decibels, but it's 0.5 in amplitude, so you don't have to pay attention too much to this number here. It's just a display in Prot. Right. And if I play it, it will play the same thing. Okay. This is a power spectrum, and that's how you're going to draw it if you have the same amplitude. If you have different amplitude, let's make one with different amplitude, maybe 1/10, right? And this one is 1/2 and 1/10. This should be okay. And oops, I need to go to spectrum. Okay, view and edit, and here they go, right? Now you can see that the amplitude of this one is much smaller than the amplitude of this one, because that's how I made it, right? And that's how you're going to draw it as well, right? But the frequency is the same, 500 and 300 hertz. Hope that is clear, and this is how you can represent or a complex wave on a power spectrum. All right. The Fourier's theorem, part 2, says that the component harmonics of any complex periodic wave all have a frequency that is an integer multiple of the fundamental frequency of the complex wave. So we are flipping on its head the greatest common denominator and saying all component waves complete an integer number of periods within each period of the complex wave. So we already knew this, but we're now making a different, a little bit different claim, right? We want to specify this as a integer multiple of the fundamental frequency, and I'll show you an example of that. But first, it would be useful to copy this on our imaginary board and say that component sinusoids, harmonics of any periodic wave, all have a frequency that is an integer multiple of the fundamental frequency of complex waves. So think about those sentences, go back and forth a little bit and think about what they're saying, right? An example is this one. Take, for example, a fundamental frequency of 100 hertz. It can only have harmonics at the following frequencies: 100 hertz, 200 hertz, 300 hertz, 400 hertz, 500 hertz. So it's an integer multiple of right, of the fundamental frequency. So it is being increased by 100 hertz by itself, right? If I create maybe a sound from a formula, what I'm going to do here, all of these will have the same one. So let me create 100 hertz, 200 hertz, then I will add a bit of 300, 400, and finally I will add up 500, right? Okay, all right, should be good. Okay, so I created a complex wave. This complex wave, if we go to spectrum to see what the component frequencies or harmonics are, we will view and edit, and we will see its spectrum here, right? Okay, maybe I changed the amplitude of these, but it doesn't really matter. We are now concerned with frequency. So this, the first harmonic, is at 100 hertz. The second harmonic is at 200 hertz. The third harmonic is at 300 hertz. Fourth is 400 hertz, and fifth is at 500 hertz, right? Don't pay attention to amplitude of this one. So these are the component waves, and this complex wave has to include them, incorporate them as such, right? Another deep thought question: what are the possible harmonic frequencies of a complex wave with a fundamental frequency of 440 hertz? If I do the following, for example, sound from, should I use the pure tone? No, from formula. What I'm going to do here now is create a 440, right? 440, this is okay. Let's see what we get here. Yeah, we get a simple sine wave. Right, I'll try to do this next time, but essentially this fundamental frequency, and I'll try to show you next time how to do this. Essentially this fundamental frequency will be 440 hertz. The second harmonic will be 880, and so on and so forth. So it's increasing for, you know, by 440, right? And it's clearly visible. For complex waves, the fundamental frequency of harmonics will always depend on the fundamental frequency of the wave, right? So the frequencies of the harmonics will always depend on the fundamental frequency of the wave, and hopefully that's quite clear, because you cannot have like 440 hertz and then have 850 hertz harmonic, no, or 980 hertz harmonic. No, you can't have that. That's the point of all of this, right? A sawtooth wave, yeah, there is a good, for example, you can do a sawtooth wave in prod by using the, let me see, this is a script, so it's easy to use script in prod. Oh, it's some more advanced for you right now, but it's easy to run them. I'm just going fast right now. Okay, this is good. Amplitude 0.5, frequency 440 I need. This is okay. Amplitude, duration 1 second. Okay, good. I'm happy with that. Sawtooth wave. Let's see what it looks like. This is a sawtooth wave. It has much more annoying sound, right? And it has a frequency of 440 hertz. Yeah. If we, so this lower display here should show its component frequencies, and that's the point of this. Let me try and get the spectrum settings a bit different. Let's see, standards, no standards. 0.5. Not really good. Let me try. Okay. Reduce a little bit the intensity. Try with this one. Yeah, this one is good, actually. This is one component frequency here, another component frequency here. You don't have to pay attention to the spectrum settings right now. This is another component frequency here. So the fundamental frequency will be 440, right? It's around here. I just cannot click on it very well. So it's here, right, as which I'm showing, 440. Then another one at 880. Another one at 130, right? 1,340, whatever. Another one for, it's increasing exponentially for, or linearly for 440 hertz, and that's the point of this. This one has 5 on display, but you know, you can go all the way. And that's exactly, this is Spectrogram showing this, which we will learn in a second, but this is exactly what you can show with this power spectrum, right? A sawtooth wave will have a lot of these. At the first one, a lot of these harmonics. The first one will be 440, the second one 880, the third one, and so on and so forth, right? And it sounds the same. Yeah, very annoying. Sorry about that. Okay. We can check out the sawtooth at sawtooth wave at 150 hertz as well. What would be the harmonics be of this one, right? So we have at 150, then then at 300, then at 450, and so on and so forth. So many more harmonics for this one, right? And it's much lower in frequency. If we go to spectrum, okay, view and edit, and there's so many more frequencies, harmonics of this one, because it's lower in the fundamental frequency. So the fundamental frequency decides or determines what kind of harmonics you will have. As I said, 150, 300, 400, and so on and so forth, right? Okay, yeah, so sorry for the switch of spots. I'm now in a phonetics lab. So another way to represent a complex sound wave is the spectrogram. It's a three-dimensional view of a sound. It incorporates the same dimensions that are found in the spectra: intensity, frequency, and time. So, for example, and on this recording of mine, the lower this the upper display is a waveform, the lower display is a spectrogram. Spectrogram shows time on x-axis, it shows frequency on y-axis, and on z-axis, something like three-dimensional towards you, it shows intensity. The darker the bars, the greater the intensity, usually, right? But here we have the darker the bars, the greater the intensity in comparison to those that are less dark. But here we have, for example, some kind of a vowel and intensity of 75 decibels, for example. And it's easy to just show intensity in prot, right? So this is what spectrogram shows and how you should be viewing it as well, right? So that's another way to represent the complex wave. One of the characteristic features of speech sounds is that they exhibit spectral change over time. What this means for us is that when we are producing sounds, we have a trilling going on in our vocal folds, and that's going to create a complex wave with a fundamental frequency. Well, we talked about that when we talked about tones, right? F goes up and down, and we can control it to some extent. That voicing will create a series of harmonics which enter your vocal folds, or your vocal tract, sorry, and the spacing between the harmonics will depend on the rate at which vocal folds are vibrating. So if my vocal folds are vibrating at 100 hertz, I'm going to have harmonics of 100, 200, 300, and so on and so forth. We can't change those frequencies, right? And this is a combination of sine waves that kind of sound like something that you've heard before. Yeah, so these are the sine waves, and this one is easy to recognize. Where were you a year ago?
Where were you a year ago?
This one is
Kick the ball straight and follow through.
Kick the ball straight and follow through.
Yeah, and this one?
The steady drip is worse than a drenching rain.
The steady drip is worse than a drenching rain.
Yeah, so they have to exhibit spectral change over time, right? In order for it to be speech. That's the point, right? They have to have some spectral change of that over time in order for it to be human speech. At least in frequency and amplitude, right? But as I said, trilling of the vocal folds creates complex wave with a fundamental frequency. This complex wave consists of series of harmonics. The spacing between harmonics in frequency depends on the rate at which the vocal folds are vibrating at our fundamental frequency, F0. We can't change the frequencies of the harmonics independently of each other. How do we get the spectral changes we need for speech? So we cannot change these frequencies of the harmonics independent of each other. So they have to, if you're trilling in 120 hertz per second, then, or just 120, if your fundamental frequency is 120, then you will have a harmonic of 120, 240, 360, and so on and so forth, right? But how do we get the spectral changes we need? So remember the two components of the spectrum: amplitude and frequency. So we cannot change the frequency, we can change the amplitude, right? And that what we do here, or we do this by changing the intensity of the harmonics. So this person is doing what we call a throat singing, right? Or harmonic singing. This person is capturing different harmonics and increasing the intensity of each harmonic. That's what you achieve with resonance. Sorry. So you can listen to this one, and I'll play it to you in a class as well. But this is essentially what this person is doing. It's capturing the harmonics. So harmonic, this level remains the same, but harmonic 2, 3, 4, 5, 6, 7, 8, so on and so forth, are being amplified, right? And when you listen to these, try and think about which vowels is this person producing, right? We'll play it again. So as we are playing this, which vowels is this person producing? Right. Yeah. Think about that, and we'll talk in our next class.